All right, so this is a thermochemistry assignment. The title is wrong, and I couldn't figure out how in AP Classroom to change the title. So this is not equilibrium, this is thermochemistry. So that's four things. Hess's law, bond energy, calorimetry, and enthalpies of formation. So we're doing thermochemistry, and that's why it's in the thermochemistry folder on Google Classroom. So this is not equilibrium. I'll have a different one for equilibrium. That is equilibrium. Okay, so let's get going on this. So question one, based on the information. So they give you two equations and two chemical equations of known enthalpies. So let's review this. The first one is saying delta H is positive 26 kilojoules per mole. That means it's endothermic. When the delta H is positive, that means the heat is going into the reaction to make the reaction go. And then the second reaction there is delta H is negative 5 kilojoules per mole. That's exothermic. Negative is heat going out, just like money in the bank. Money going in is positive, money going out is negative. So what they want you to do is create, using those two reactions, create the one they have down there below. I2S goes to I2G. So it's a fairly simple one. So what you have to do is, you see, where is I2S up there? It's in the first reaction, and it's on the left side of the arrow, which is what you want. And so you can leave that one for right now. What about I2G? It's in the second reaction, and it is on the left side of the arrow, but you need to have it on the right side of the arrow. So you need to flip that second equation around. And once you do that, you're going to reverse the value on the delta H. So it goes from negative 5 to positive 5. Now the other thing that you have to do is the I2S, in the two equations up above, the I2S has got a 1/2 coefficient and the I2G has a 1/2 coefficient. That means you need to multiply both reactions through by 2 because you have to get rid of those 1/2s. So you have to end up with I2S with a 1 coefficient goes to I2G with a 1 coefficient. So again, let me repeat what you're going to do. You're going to turn the second equation around so the 1/2 I2G goes over on the right side of the arrow. And then what you got to do is multiply both equations through by the number 2. So that means on the top equation, you're going to have 2 times 26 is 52. And on the bottom equation, you turn the negative 5 into a positive 5 by flipping the equation around. And now you have to multiply that by 2. That'll give you 10. So if you add 52 plus 10, you get a positive 62. And that would be the answer. And there it is down there. Okay? So flip the bottom one around, turn it around, and multiply both of them through by 2. And that's the idea between Hess's law. Again, this is on the video on thermochemistry in the Google Classroom now. All right, let's keep going. Try to get through these fairly quickly. All right, according to the information above, what is the standard enthalpy of formation for NH3? So remember, standard enthalpy is the enthalpy required. Standard enthalpy of formation is the enthalpy required to create exactly 1 mole of a compound from its basic elements in their most stable form, or in their standard form. So all three of these, NH3, H2, and N2, are all gases in their natural form at 298. So what you're going to do is, first of all, if you're going to create NH3, it's got to be on the right side. It's got to be on the product side. So you're going to turn the entire equation around, and that's going to make the 92 kilojoules per mole become a negative 92 kilojoules per mole. So now on the left side you have 3H2 plus N2, and then on the right side of the arrow you have 2NH3, and because you turn the equation around, you turn the 92 into a negative 92. Now we need to have that just be 1 mole of NH3, so that means we have to divide the entire equation through by 2. So if you take negative 92 and divide it by 2, you get negative 46. And so then you would have a reaction. You would have to divide everything through by 2. So you'd have a reaction that would be 3/2 H2 because you divided by 2, plus 1/2 N2 because you had to divide that by 2, will give you NH3, 1 mole of NH3, and that's exactly what you want. And and then you divide the negative 92 by 2 as well. So you get negative 46 for that. And there we go. Okay. Next one. Whoops. Okay, here we go. What is the standard enthalpy change for the reaction represented above? So this used the enthalpy of formation method to do this, and that means you take the enthalpy of formation of the products minus the enthalpy of formation of the reactant. So the enthalpy formation of C6H6 minus the enthalpy of formation of 3 moles of C2H2. That means you have to multiply that number by 3. So the enthalpy of formation of C6H6, they give it to you there, and that's 83. And then that's going to be minus 3 times 230. So 3 times 230, and it's negative 230, because you're subtracting it. I'm sorry, it's 3 times 230, so you're subtracting it though, and that gives you 690. So it's 83 minus 690. 83 for the product, C6H6, minus 3 times 230 for the reactants, and that gives you negative 607. Okay, and there's that answer. Okay. All right. If the standard molar heats of formation of ammonia and gaseous water are negative 46 and negative 242, what is the value of delta H for the reaction represented above? So again, it's an enthalpy of formation method. So you're going to take everything on the right, that's 2N2 plus 6H2O. You're going to add those together, and then you're going to subtract the reactants. So that's 4NH3 plus 3O2. You're going to add those together, and you're going to take the products minus the reactants. So first of all, the enthalpy of formation of any element in its natural state is 0. So the O2 is going to be 0 and the N2 is going to be 0. So it doesn't matter what the coefficients are in front of them. Again, O2 and N2 are both 0 because they're elements in their natural forms. So the only things you have to think about are the water and the ammonia. So it's 6H2O, and they gave you that number as negative 242. And that gives you negative 1,452 kilojoules per mole. And then you subtract for that the number for ammonia, which is 4 times negative 46. So be careful. It's minus a negative. I'm going to go ahead and write this out for you. Okay, so here it is. So this is the H2O. This is the N2, and it's 0. And then you subtract from that, these are the products, you subtract from that the reactants. So this is minus all of this, so it's 4 times negative 46 for NH3 plus 0 for the O2. Okay, so when I take the enthalpy of formation of water, and there were 6 moles, the nitrogen has an enthalpy of formation of 0, so there's nothing there. Then you subtract, these are the products, and then you subtract the reactants. So the enthalpy of formation for ammonia is 4 times negative 46. There are 4 moles of it. And you're going to subtract that, so that's going to end up being a positive 184. And then this, of course, is 0. So you add that up, and you get negative 1268 for your answer. And that's kilojoules per mole. And so we come back and, well, I see negative 1270. That's close enough for me. I don't know why I was off by 2, but anyway, that is the correct answer. Okay, so it might be a significant figures. Yeah, it's a significant figures issue. Well, I'm going to say it's a significant figures issue. I don't know. Anyway, it's close enough. That's the only answer that's close to what I got, so I'll take that. All right, let's keep going. Okay, the enthalpy change for a reaction represented above is delta HT. This reaction can be broken down in a series of steps in that diagram. The relationship that must exist are, well, you can see that if you start at A and end up at X, you can go one of two routes, either delta HT, or you can add three different steps together, delta H1, delta H2, and delta H3. So that means delta H2 must equal delta H1 plus delta H2 plus delta H3. And you don't really see that answer down below. But what you do see is delta HT minus delta H1 minus delta H2 minus delta H3 equals 0. That's the same as what I just said. And so that would be the answer. Okay. All right, a 10 gram cube of copper. Notice they have a decimal point there. That means it's two significant figures, if that were important, but that's why they put the decimal there. A 10 gram cube of copper at a temperature of T1 is placed in an insulating cup containing 10 grams of water at a temperature of T2. If T1 is greater than T2, so they're saying the copper is hotter than the water. That means the heat is going to flow out of the copper and into the water. Which of the following is true of the system when it has attained thermal equilibrium? The specific heat of copper is 0.385 and the specific heat of water is 4.18. The temperature of the copper changed more than the temperature of the water. We can check that out. The temperature of the water changed more than the temperature of copper, so those are your two options. The temperature of the water copper changed by the same amount. The relative temperature change of the copper and the water cannot be determined without knowing T1 and T2. Well, we can at least try. We can write the equation. So the amount of heat out of the copper, so this is copper. I'm going to do this one down below. Okay, so what we're going to do is figure this out given the numbers they gave us. So anytime you have to relate heat to temperature, you use this equation. It's really the most important, maybe the only equation in thermochemistry. This relates heat and water. So what do we know? We know that the amount of heat that went out of the copper went into the water. So since heat going out of something is a negative value of Q, negative heat, then the same amount of heat went into the water, so it's the same number, but with a positive sign. I'll even put a plus sign there. So it's plus Q minus Q, but it's the same numeric value. So what do we know about the relationship between that amount of heat and the temperature of the copper? So this is the copper, so it's 10 grams of copper, and that was the specific heat of the copper, and you multiply that by however much the temperature of the copper changed. That's what we're kind of trying to find out here. For the water, it's the same number except positive, but that's not really relevant. It's the numeric value is the same, equals 10 grams of water, and there's the specific heat of water. So if these two are just equal and opposite, we can set them equal to each other. If you want, you can put a negative sign in front of one of them. It doesn't really matter because we're looking for a kind of a relationship value here. So if these two are equal, I can set these two equal to each other. And so I do that down here. 10 times 0.385 equals 3.85 times the temperature of the copper. And 10 times 4.18, the specific heat of water, equals 41.8 times the temperature of the water. And those two, again, if I want to put a minus sign in front of one of them, that's fine. But it's not really important. So now what you can do is you can either solve for TC or TW. It doesn't matter. So I'm going to go ahead and solve for TC. So I'm going to divide both sides by 385. Divide by 385. And what I end up with is the change in temperature of the copper is 10.9, basically 11 times the change in temperature of water. So as you know, water's temperature doesn't change very easily. You put a cup of water outside on a cold morning and feel it, and then feel it in the afternoon when it's hot, the temperature of the water doesn't feel that much different. You can stick your finger in when it's cold and it doesn't freeze your finger off, and you can stick it in when it's hot and warmer later, and it's only kind of lukewarm. It's not really all that warm. So temperature of water doesn't change very much compared to the temperature of the metal. So let's say the water changed by 2 degrees. That means the copper changed by 22 degrees. So that makes sense what this equation is telling us. So the temperature of the copper is going to change a lot more than the temperature of the water. So we'll go back to the question. And it says, A, the temperature of the copper changed more than temperature of water. Well, that's what we just determined by doing that. So there's your answer right there. Okay? All right. A 1 gram sample of a cashew was burned in a calorimeter containing 1,000 grams of water, and the temperature of the water changed from 20 to 25. So you have a delta T, you have a mass, you know it's water, so it's 4.81 is the specific heat, so you can figure out the heat. In another experiment, a 3 gram sample of marshmallow was burned in the calorimeter containing 2,000 grams of water with a temperature change. So you can do the same thing a second time with the marshmallow. Based on the data, which of the following can be concluded about the energy content for 1 gram of the two substances? Okay, so we'll go ahead and set up that equation. Okay, so first we're going to figure out how much heat was released by the cashew. And the confusing part of this for students is which mass to use. They told you the cashew was 1 gram, but they told you that you had 1,000 grams of water. So what you're going to do is figure out the heat that goes into the water. We're trying to figure out the heat coming out of the cashew, but we can't do that directly. So we have to figure out the heat that's going into the water. So you're going to use this equation. So everything that you're going to figure out has to do with water. So the mass of the water is 1,000 grams. The specific heat of the water is 4.81, and the temperature change was 5 degrees. I don't remember from what to what, but it was 5 degrees. There was a 5-degree difference. So if you calculate that, you figure out the heat that went into the water was 20,900 joules. So that's how much heat had to come out of the cashew. So now that you know the heat that went into the water, and therefore the heat that came out of the cashew, you can figure out how many joules per gram comes out of the cashew. So divide that number by 1 gram. So this is the mass of the water here that you use to first figure out the heat. And this is the mass of the cashew that you want to figure out how much heat per gram, not of water, but of cashew. Okay, there it is. So you get 20,900 joules per gram for a cashew. Now let's do it for the marshmallow. Again, you've got to figure out the heat going into the water first. There's 2,000 grams of H2O. Same specific heat, same temperature change. So that gives you 41,800 joules of heat coming into the water, going into the water, because that's what you just figured out, is heat going into the water. That has to be the same amount of heat, though, that came out of the marshmallow. That's where all the heat came from. So that's what you got in the water. More than for the cashew, but if you want to figure out how much heat per gram, because you're trying to compare apples to apples, how much heat per 1 gram, you have to divide that by 3 grams. So this is the mass of the marshmallow. That's M-A-R, that's marsh. Okay, and this is mass of water. So if you divide 41,800 by 3, you get 13,933 joules per gram. So you get more joules per gram of heat out of a cashew than you get out of a marshmallow. So let's go back and see what the question's asking. That the combustion of 1 gram of the cashew releases less energy. No, it releases more. Okay, let's go back and look. It releases 20,900 per gram, whereas the marshmallow releases only 13,933 joules per gram. So the answer, so A is not correct. The combustion of 1 gram of the cashew releases the same amount of energy. No. The combustion of 1 gram of the cashew releases more energy. Yes. So that's the answer. It should be. Yes. Okay? So there you go. So again, this is a calorimetry problem. So let's be sure you understand the basics of calorimetry. You want to know how much energy is in this object. You can't measure it directly. All you can do is burn it. And you burn it in such a way that all of the heat is released into the water. So you know all of the heat, therefore all of the energy from this went into water. So you got to figure out how much heat went into the water. So you use the mass of the water, the specific heat of the water, and the temperature change along with this equation to figure that out. Now that you know the amount of heat that went into the water, that has to be the amount of heat that came out of the cashew. All the heat that went into the water had to come from the cashew. So this is both the heat that went into the water and the heat that went out of the cashew. So now if you want to know how much heat came out per gram of cashew, you divide that number by 1 gram for the cashew. For the marshmallow, again, same thing. You want to figure out how much heat from the burning marshmallow goes into the water. So this is the grams of water. Specific heat, temperature change. This is how much heat you got out, how much energy you got out from the marshmallow. Now you want to know how much heat per gram, because you want to be able to compare 1 gram of cashew to 1 gram of marshmallow. And you divide that by 3 because there were 3 grams of marshmallow. And you get a lower number for the marshmallows, 13,933 joules per gram. So therefore, the cashew released more heat. Okay, next question. Okay, a sample of a metal was heated to 100 degrees and then quickly transferred to an insulated container holding 100 grams of water at 22 degrees. And that's pretty close to room temperature. The temperature of the water rose to reach a final temperature of 35 degrees centigrade. Which of the following can be concluded? Oops, I left the answer up. I didn't mean to do that. Which of the following can be concluded? The metal temperature changed more than the temperature of the water did. Therefore, the metal lost more thermal energy than the water gained. Okay, everything about that statement is true, except the very last part. The amount of thermal energy has to be equal. The metal has to lose the same amount of thermal energy as the water gains. The temperature change is going to be different, but thermal energy is heat. And the heat going out of the piece of metal has to be the same as the heat going into the water. So to say the metal lost more thermal energy than the water gained is not true. That part of A is not true. B, the metal temperature changed more than the water temperature, but the metal lost the same amount of thermal energy as the water gained. That's true. We just saw that was the answer, so that is correct. They both lose the same amount of thermal energy, or gain the same amount, lose and gain, but the temperature of one will be greater than the temperature of the other due to the fact they have different specific heats. The metal temperature changed more than the water did. Therefore, the heat capacity of the metal must be greater. No, heat capacity, just learn this, heat capacity of metal is very low. Heat capacity of water is very high. Final temperatures, anyway, let's move on. We got the right answer. It was B. Okay. All right. A hot iron ball is dropped. These are very similar problems. A hot iron ball is dropped. They're problems that are reasonable for them to give you on this subject, too. A hot iron ball is dropped from into 200 gram sample of water, initially at 50 degrees. If 8.4 kilojoules of heat is transferred from the ball to the water, what is the final temperature of the water? So all you're going to do is take this equation, Q equals mc delta T, and just rearrange it so it's solved for T. Okay, so down there's the equation we have, but they want to know the temperature change. Okay, so let's go ahead and let me write all that down. So it's going to be delta T is Q. It tells you that's 8.4 kilojoules. Down on the bottom we have the mass of the water, which is 200. And we have the initial temperature of the water. So the temperature change, so let's talk about this. So here's the equation. And the specific heat of water is they said use 4.2 in this problem. 4.2. Now temperature change. Another way of saying temperature change, delta T, change in temperature, equals the final temperature minus the initial temperature. T final minus T initial. So they gave us the initial temperature as 50. So it's going to be T final minus 50. So you got a little bit of an algebra problem here, not much. So it's going to be 8.4 divided by, and you got to be careful here. Hang on a second. Let me go back. The specific heat is measured in joules. So you got to be careful. You will totally miss this answer if you don't do this. You got to convert the kilojoules to joules. So I'm going to go back here, and I'm going to change this 8.4, I'm just going to do it right here, to 8,400 joules. Okay, because that's what this constant, this specific heat constant is in. Okay, so let's go do it again. 8,400 divided by 200. divided by 4.2 equals 10. So that means TF minus 50 equals 10. So if I add 50 to both sides, I get TF equals 60. And there's the answer right there, 60. Okay? All right, so let me go back and show you the equation one more time. You can see that. So that means this has got to be 60. 60 minus 50, and all this became 10. Okay? All right, let's keep going. All right. And I don't mean to show you the answers too quickly. Okay, a molecular solid coexists with its liquid phase at its melting point. Okay, so the melting point is where it changes from liquid to solid. The liquid-solid mixture is heated, but the temperature does not change while the solid is melting. The best explanation for this phenomena is that the heat absorbed by the mixture. Okay, so I showed you this graph for ice, and it could be for anything. It doesn't have to be for ice. And it looks like this for ice. So let's say you're at minus 20 degrees here, and 0 degrees, and 100 degrees, and let's just say 120 degrees. And this is all centigrade, okay? So when the ice is down here, and you start putting heat, it heats up, the ice heats up, but it doesn't melt. It stays ice as long as it's below 0 degrees. So it heats up until it gets to 0. And then, while the ice is melting, it all stays at 0 degrees while it's melting. So this is ice, this is melting, and with that heat that causes it to melt from ice into water is called the heat of fusion. Once the ice entirely melts, it continues to heat up as liquid water, until it gets to 100 degrees. And then the water starts to boil. And while the water is boiling, it stays at 100 degrees. So while it's changing phase, the line is flat. That's supposed to be a flat line. And that's called the heat of vaporization. Once it all becomes steam, then you can start heating it some more and make it go up above 100 degrees. Okay? So what they're talking about for this particular question is this area right here where it's melting. And the reason the temperature stays the same is because all of the heat energy is going into breaking the intermolecular attractions between the molecules, so that they go from sticking really tightly together as a solid to being kind of loose. They're still sticking together as a liquid, but they can move around each other, so they're looser. So all of the heat is going into loosening or reducing the intermolecular forces. It's not breaking chemical bonds. If this was water, it's H2O, H2O. It's the same stuff. But it's the forces between the water molecules. So let's go and look at the answer here. So it says the best explanation for this phenomena is loss to the surroundings. That's not it. Is used in overcoming intermolecular attractions in the solid. That's it. Okay, it's causing the ice to melt into liquid water, and that means there's weaker intermolecular attractions, and the energy overcomes those. So there's the answer for that. Okay? All right. Next. All right. Oh, picture problem. A student is asked to determine what mass of butane needed to burn in order to raise the temperature of a 1650 gram beaker of sand by 180 degrees. Okay, this is interesting because it's not water. The student is provided with the equipment shown below. All right. Now, why would you use a beaker of sand? Well, you can't burn butane in water. So you're putting the butane in the sand, and then you're lighting it on fire. So this is interesting. There it is. So there's the whole situation right there. Oh, I see. No, so the butane is not in the sand. I'm sorry. Okay. So it's down below in that butane burner. So you're going to measure the temperature increase, and you're going to measure how much butane you used. Okay, so let's read the question. Calculate the amount of heat needed to raise the temperature of the beaker of sand by 180 degrees centigrade. Assume that all the heat energy from the burner is transformed to the beaker of sand. Okay, so you didn't lose any. That would never be the case, but let's just pretend. And the specific heat capacity of the beaker and the sand together, because you have to treat the whole thing, not just the sand, is 0.810. Okay, so calculate the amount of heat energy. So, okay, so question A says calculate the amount of heat energy. All right, so let's go down to our sheet here. And you use the same equation. They told you that the mass of the sand and the beaker is 1650 grams. They gave you the specific heat of the beaker and the sand. And the temperature difference, it went from 200 to 20. So you multiply those all together, and you get 240,000.5 or 500 joules, but we'll convert that into kilojoules. Now they are asking you about, down in a lower part of this question, they're asking you about significant figures. So significant figures, when you do a subtraction, it's 200 minus 20 is going to be 180, and that's going to be three significant figures, 180. When you do a subtraction, it's that would be three significant figures. Then when you do multiplications, it's the number with the least number of significant figures. So this is 3, this is 3, and this is 4. So the answer can have three significant figures. So that would be the answer to that. Now, you usually don't do significant figures until you get to the very end, but here we did. Okay, anyway. All right. Okay, so we're going to use Q equals MC delta T. The mass of the beaker and sand, that's what's catching all the heat. That's what you're measuring heat in, coming into, is 1,650 grams. It tells you that the specific heat up here in the sentence is 0.180 joules, gram centigrade, so up there where the cursor is. And finally, that's the specific heat, and the temperature change is from 200 to 20. So that's going to be 180 degrees temperature change. All right, so we go over to the camera, and there it is. I plugged in those numbers, mass, specific heat, temperature change, and I get 240,500, which at three significant figures, because they're going to ask that down below, I didn't mention that, is going to be 241 kilojoules, 241 kilojoules. So that's the answer to A. So in part B, they ask, calculate the number of moles of butane that was used. So you have the mass of the butane in the burner before combustion and after combustion. So the difference in those two is the amount of butane that was used. So it's 225 minus 0.26, 225.2, excuse me, so let me say that again, 225.26 minus 218.20. And if you do that, you get 7.06 grams of butane were used. Now you have to do the molar mass for butane. Butane is C4H12. You can use round numbers on the AP, so C4 is 4 times 12 for carbon and 10 times 1 for hydrogen, so that's 48 plus 10 is 58. So if I go down to my paper here, so there's the mass of the butane that was burned. So now you take the molar mass of that, find the moles of that, there's the molar mass right there, 58 grams of butane for 1 mole, so it's 0.12 moles. So that's the answer to B. Okay, part C says, using the balanced equation for butane, determine the amount of heat energy produced by the combustion of butane in the experiment. Well, you can see from that balanced equation that 1 mole of butane, because that's how much you have in that equation, C4H10 is 1 mole, produces 2,659 kilojoules per mole. So 1 mole produces 2,659 kilojoules. Okay, so we go back to our sheet, and we just calculated that we have 0.12 moles of butane. So if you take 0.12 moles, I won't write butane every time, times 2,500, what was it? 2,659 kilojoules per mole. Moles cancels and you end up with kilojoules. And that gives you 300, and if they're worried about significant figures, it's 319. That's how much energy was produced by the butane in this specific experiment. Okay, that's how many moles were used, and that's how many kilojoules per mole. All right. Okay, Part D. The student claims that some of the heat energy produced in the combustion of butane was lost to the surrounding air system. Do your answers in Part A and C support the student's claim? Yes, they do. Okay, let's go back to here. So this is the amount of heat the student actually measured based on how much heat went into the sand of the beaker, specific heat, and the temperature change. He measured this much heat. But based on theory, he should have gotten this much, based on how many kilojoules per mole you get out of butane and how many moles he knows he used up. He should have gotten this much. This is called the theoretical yield. It's what you should have gotten based on, I used this much butane, and this is the measured known value for kilojoules put out by a mole of butane. This is what you should get. But he only got this much. So this is called the actual yield. This is called the theoretical yield. And so, yes, in that experiment, a lot of the heat would be lost to the atmosphere. So the theory says he should have gotten this. His actual measured value was a lot less. So yes, that would explain it, that he lost heat to the atmosphere. Okay. All right, I'm going to cut this off now. I think there's one more question. I'm going to go ahead and cut this off now. Again, this was thermochemistry, not equilibrium. I mistitled it, and I don't know how to retitle it. So just be aware of that when you go to the Google Classroom. It will be in the thermochemistry section. And you can do this online in the AP classroom. Okay, take care.